We're now ready to begin Chapter 6, where we will start covering rational functions. Now, in college algebra, our biggest goal and objective will be to set up equations that model real-world events and to solve for unknown quantities in those equations. Throughout the chapters that we cover in this course, we will look at several different types of expressions of functions of equations. We're going to begin by looking at rational functions, whereas in polynomials, which we covered in that Chapter 5 review, only allowed us to handle certain types of functions. We're now going to enter a set of functions that allow us to have variables in the denominator. So when we look at these expressions, we're going to have basically fractions showing up in the problems where the variables are either in the numerator or in the denominator. So in section 6.1, the very first section, we're going to begin by talking about what that term rational actually means. What is a rational function? And then describe its domain. And then how do we multiply and divide rational expressions? Here we are in 6.1. We're ready to begin talking about the domains of rational functions. Let's begin by just giving a definition for what a rational expression is. A rational expression, by definition, is the following. It consists of a polynomial divided by another polynomial. So in essence, we're going to be looking at expressions that have a polynomial in the numerator and a polynomial in the denominator. A very simple example might be something like 5 divided by x, where 5 as a constant could be thought of as a monomial, as a single term polynomial. You have x in the denominator. Notice this does not meet the definition of being a polynomial because there's variables in the denominator. But now that we're talking about rational expressions, that's what it looks like. We also could do something like 120x divided by 100 minus x. Again, we have a monomial in the numerator. In this case, we have a binomial, a two-term polynomial in the denominator. Or even more interesting, we might have a full, like say a trinomial, 3 terms in the numerator. X squared minus 7x minus 18. All of this is divided by 2x squared plus 3x minus 2. These are just formulas, expressions that might represent real-world quantities, but in this case, notice that they have shown up in this fraction form. Okay, so that's what a rational expression is. It's an expression. Now, if we want to talk about a rational function, which is the title of the chapter, we need to know, okay, just as a quick reminder, what is a function? Now, function in mathematics is a special object that we often represent with a formula. It basically assigns a single output to each input. So a function has an input and an output. This would be an example right here of a polynomial function because the formula for that function, that is the right hand side, is a polynomial. And remember, we talked a little bit about this in the Chapter 5 review. What this means is that whenever we take a particular value and plug it in for x, say f of 2, that would mean to substitute in everywhere there's an x with 2. So that would be 2 squared plus 2 times 2 plus 3, which we could work out to be 4 plus 4 is 8 plus 3 is 11. Notice how the input was 2, the output is 11. So a rational function is going to be a function whose formula appears like one of these. That is, it is rational. Now, just as an easy way to remember this, from this point on, anytime in a math class you see the word rational, what we mean is almost always this is the same thing as fraction. Okay? When you hear rational, think fraction. Whenever we discuss new types of functions, the first question we want to answer is what is the domain of that function? By domain, we're saying what numbers are we allowed to plug in. Most of the functions you've probably seen up to this point, we could plug in anything we want. But there is a restriction on rational functions that we need to talk about. So the domain of a rational function is going to be the set of all values except those that make the denominator 0. Now realize that that's a problem whenever we have 0 in the denominator, a problem we're going to talk about here in just a minute. Now the notation we're going to use for domains, whenever we say, okay, what numbers can we plug in, we're going to use set notation. Because in mathematics we always denote sets with curly braces, and I'm going to use something called set builder notation, which looks like this. We're going to say that the domain of a function is going to be the set of all values for the variable x that I can plug in such that x is not equal to, and then I'll have a list of values here that it can't be equal to. So this is read as the set of all x. This little line right here means such that, so I'll say such that x is not, and then whatever we have listed there. That's how we would read that. So that's how we're going to write our answers when we start answering the question of what the domain of a rational function actually is. Here is an example of a particular model equation that uses a rational expression, so it's a rational function, and a couple of questions we want to be able to answer and interpret what our answer actually means. So we're given this problem that says that there is a cost-benefit model, f of x is equal to 120 times x, all divided by 100 minus x. We're told this models the cost where the output of the function is in thousands of dollars, and that's how much it costs to remove X% of pollutants that the city has discharged into a lake. So we want to find and interpret each of the following. We're asked to find f of 20, and as I mentioned before, what that means in a function is to actually plug this value, the 20, in for x right here. So we're going to take 120, and instead of x, we're going to put 20 in. We're plugging that in as our input, divided by 100 minus 20. So 120 times 20. I'm going to pull out my calculator. Remember, I recommend that you have a calculator for this course because a lot of the computations we're going to do in here will require it, and also will just aid your process along to speed up your homework a little bit. That's going to give me 2,400 or 2,400 on top, divided by 80. We can actually do this pretty quickly in our heads. The answer is 30. Now what that means is it costs $30,000, because the output was in thousands of dollars, to remove, and remember it's X%, so when we plugged in 20, we mean it costs that much to remove 20%. Similarly, if we plug in 80, we're going to get 120 times 80 over 100 minus 80. So 120 times 80 gives me 9,600 divided by 20. That's 480. So interpreting that says that costs a whopping $480,000 for the city to remove 80%. So the more you want to remove, the greater the cost to you. Okay, so that's how we might use a function like this, is that a particular model has been set up for us that we are then able to use. Again, let me note this. When you write down a rational expression, we're always going to assume that the values that make the denominator 0 are excluded, right? You cannot divide by 0. Now, you've probably been told that over and over, but have you ever asked yourself the question, why? Why is that true? Why can we not divide by 0? I mean, if I write down something like 5 divided by 0, why is that, say, not 0 or nothing? You know, whenever I ask this in my face-to-face classes and I have students sitting in front of me, I make them answer that. Why is 5 divided by 0 not anything? What's the problem with that? And one way to think of this is to remember that if you ask the question of, say, 8 divided by 2, what you're basically doing is taking 8 and breaking up into pieces of size 2 and asking how many pieces do you have. Or another way of thinking of it is 2 times what gives me 8. You're asking for that missing piece right there. Well, if you phrase the original question of 5 divided by 0 that way, you'll have 0 times what is equal to 5. And so what can you put right here? What can you stick in where that question mark is and say, well, that's the answer. That's what times 0 gives me 5. And you clearly see nothing works. Not even 0 works. It's not 0, because if I put in 0, that's still not true. 0 doesn't equal 5. But if I put in a 5, a 6, a 10, a minute, infinity, still I can never get to the 5 in this particular form that we have here. So whenever we see something divided by 0, recognize that that is not a number. There is nothing that you can get by dividing by 0. we are asked to identify the values that are excluded in this example. So looking at this function, what things are we not allowed to plug in? What's excluded when I write down this formula? Well, the answer is it's whatever makes the denominator 0. So I'll set 3x minus 12 equal to 0. That's how I'm always going to find the domain of these functions, is set the denominator equal to 0. That way I can figure out what values satisfy that statement, and those are going to be the values that are excluded. So I can add 12 to both sides. 3x equals 12. Divide both sides by 3, and that gives me x is equal to 4 is excluded. That's how you would write that answer. Those are the values that are excluded. Similarly, on this one, example B, we are still asked to identify those values that are excluded. So again, I want to know what can I not plug in. Anything that I plug in here that would make the denominator 0 would be a problem, right? So 2x squared minus 15x plus 25, set that equal to 0. You'll recognize that as a polynomial equation, which means we solve polynomial equations the same way. Every time we get them equal to 0, and then we factor and set each factor equal to 0. So this is now a factoring problem. This sign, the second sign, tells me that the signs are both the same, and the other sign tells me they're both minus. I'm going to put a 2x and an x here. That's the only thing that multiplies together to give me x squared. And then for the last terms, we can do 1 and 25. I think 5 and 5 work the best, right? Because then the outside is minus 10, and the inside is minus 5. That's minus 15. So that's good. Set each one in. So I set each one here equal to 0. 2x minus 5 equals 0, and x minus 5 equals 0. Adding 5 to both sides on this one gives me 2x is equal to 5. Divide both sides by 2. X is equal to 5 halves. Adding 5 to both sides on this one gives me x is equal to 5. So these two values are both excluded. Anything else you plug in is perfectly fine. If I plugged in 2, 7, 12, 35, 1 million, no problem. But if I plug in 5, it doesn't work because the denominator is 0. There is no value for that formula. On the next set of examples, we have basically the same question, but it's asked in a slightly different way, so our answer is going to be in a different form. In this case, we're asked to find the domain, right? In the last question, we were asked to find what was excluded. Now we're asked to find the domain. So the domain, we're going to go back to that notation that I introduced to you previously for using sets to answer this. But it's the same approach, because we're still going to set the denominator equal to 0 to find out what's excluded. So minus 8z plus 4 equals 0. If I subtract 4 from both sides, alright, I'll have negative 8z is equal to negative 4. Divide both sides by not negative 4, I want to move the 8 over, so divide both sides by negative 8. Right, and then simplify that. I get z is equal to 1/2. Now, to write that, I'm going to write it this way. I'm going to say the domain, we'll call it D, is equal to the set of all z's such that z is anything but 1/2. That is not equal to 1/2. And that is how I will write my answer for that. I think on the online homework, you'll be asked to kind of fill in the blanks on this, but it's important that you understand what that notation actually means. Next example, example B. Same deal. We're going to now set a squared minus 49 equal to 0. It's polynomial because we've got squares involved, so I can factor this. We remember that we factor a difference of squares as the square root of each of these added together and subtracted together. So it's a plus 7 times a minus 7. I'm going to set each of those equal to 0. A plus 7 equals 0. That tells me a is negative 7. And a minus 7 equals 0 tells me a is positive 7. So the domain for this would be the set of all a such that a is not equal to negative 7 or positive 7. And that's the domain of that function. Those are the numbers where it has dominion, right? If you think of it as a kingdom, the function has certain dominion over numbers. These are numbers it doesn't have dominion over. You can't plug in negative 7 and positive 7. Those can't possibly be inputs. Okay? So we've got the domain nailed down. Next thing we're going to talk about is How do we simplify? We take a rational expression, we want to reduce it. Just like if you take a fraction that's reducible, you want to be able to reduce those fractions. We're going to do the same thing now with polynomial fractions or rational expressions. The basic steps to simplifying a rational expression are just the following. You're going to factor the numerator. You're going to factor the denominator. And then you're going to cancel out common factors. In instance, what you need to remember when you're simplifying is factor then cancel. By cancel, we mean they divide each other out, right? They're gone. You can kind of mark them out, basically. So, for example, on this example, on this particular problem right here, we're going to first factor the numerator. Okay, we know it's plus and plus, x and x. The only choices for 3 are 1 and 3, and double check that. Does it work? We have 3x plus 1x is 4x. Yep, that works. All divided by x plus 3. Okay, now we're going to divide out the common factors. Notice how they're both in common. We can cancel those out. We can divide them out. Okay, that leaves me with x plus 1. That's my final answer. Okay, let me make a point here, and I'll make this again just for reiteration later. I'm going to make it now. I'm going to make it over and over again. You may be tempted to see something like this 3 here and this 3 up here and think we can cancel those. Now, the reason we can't do that has to do with the plus sign right here and right here. When you slash these things out, like I've done with the x plus 3 here, what you're basically saying is x plus 3 divided by x plus 3 is just 1, and 1 times anything is itself. So that's why this is the same thing as x plus 1. Now, over here, you have a plus 3 on top and a plus 3 on bottom. Okay? They're not divided by each other. In fact, it's this whole thing here that's divided by this whole thing here. It's not the 3 divided by the 3. Okay? It's the plus sign that means you can't do that. So here's what you should think. When you see plus signs, okay, in the numerator, or you see minus signs in the numerator, think mortar between bricks. Those things are stuck together and you can't break them off. They're stuck to the rest of that numerator, that denominator. The only thing you can break is multiplication. Multiplication snaps right off, right? That's just, it's like snap-on tools. They just snap, right? They snap right off. Okay, I don't think snap-on tools actually snap. So if you have snaps, what kind of toys you play with when you're a kid that have like snap-on pieces and things like that? Whatever. Snap, you know what I mean. Breaks off in half, right? So this thing breaks. Multiplication breaks. Addition and subtraction, they're stuck. You treat those as a whole object, okay? So do that on the next one. But I'm going to get rid of some of this mess. Sorry, hold on a second. There, we got that cleaned up. Okay, next problem. Same first step. We begin by factoring. So I'm going to factor the numerator, and I'm going to factor the denominator. So we know this is plus and this is minus. We have x and x. I think it's going to be 2 and 9 that works, right? Minus 9x plus 2x is minus 7x. This one is going to be also plus and minus. We're going to have a x and a 2x. Let's go with 2 and 1. And that's minus x, and positive 4x gives me plus 3x, so that works. Now, what do you see in common? Right, you see them? This is the same right here as this. So whenever you see them in the same, you can cancel them out, and you're left with x minus 9 over 2x minus 1. Yes, I did do sound effects, by the way, whenever I was slashing them out. It adds a little excitement and adventure to algebra if you have sound effects while you're doing this. So I get a little excited while I'm teaching this. I enjoy myself. You need that from a professor, I hope. Anyways, this cancels completely out. That's just 1, so it's gone. I'm left with this as my final answer. Voila! Da-da-da! That's how we simplify rational expressions. Now, I want to back up and point out something real quick here that needs to be focused on, just so that you're aware of this. It's very possible that you could have two factors, one in the numerator, one in the denominator, that are alike in every way except all of the signs are opposite. For example, look at the C that you have right here, example C. Notice in both the numerator and the denominator I have a 5r, and in both the numerator and the denominator I have a 4. But if you look at the signs that are out in front of that, in this case this minus sign here, this 4 right here is a positive, right? I mean, that's understood to be a plus 4 right there. On the other hand, if you look at the sign in front of the 5r, it's a minus sign here. What's understood to be right here? Well, if there's nothing there, it's understood to be positive. Notice how all the signs are opposite. Same terms, but all opposite signs. Now, what do we do in that case? Well, in that case, what we're able to do is take either the numerator or the denominator and factor out a -1. So let's say, for example, we look at the denominator. We could rewrite the denominator in the following way. In fact, watch me do this. I'm going to take the 5r minus 4 that's in the numerator. In the denominator, I'm just going to switch the order, because it doesn't matter what order I do this in. I'm going to put a minus 5r and a plus 4, right? Because addition commutes. You can change the order of addition. And again, you can see even better now how the negative sign is opposite on top and bottom, and the same thing for this for the 4. We got -4 on top, +4 on bottom. So what I mentioned in the note here is we can actually factor out this -1. If we do that, here's what we end up with. On top I have a 5r minus 4. On bottom I'll take out a -1. Okay, and factoring that out leaves me with 5r minus 4. Notice how taking out a -1 just changes the sign of everything. And these are now exactly the same, and I end up with 1 over a -1, which is just 1 divided by -1, which is a -1. So notice how whenever you have all the same terms but opposite signs, it factors out, it cancels out, and leaves behind a -1. One thing that you also have to be careful of is it's incorrect to divide out common terms from the numerators and denominators. We've mentioned that we've canceled out these factors. It's important that you know that factors are those things that are connected by multiplication. Terms are connected by addition or subtraction. So notice, for example, if I have x plus 4 over x, okay, what we're not allowed to do is we cannot cancel out this x and get a 4. That does not work. Okay, that is not allowed. Now, why not? Why can't you do that? Well, we've mentioned it before. That plus sign is like mortar. It's holding that plus 4 to that x. And whenever you cancel, what you're basically doing is dividing by that bottom factor. And whenever you divide by something that's equivalent, you end up with a 1. Now, here's the thing. Whenever we have this division right here, if I take this x plus 4 and divide it by x, that division doesn't cancel this x out because of the way that x is connected. Right? Division cancels multiplication. It does not cancel addition. So that's why you can't do that. You also couldn't do it if, say, for example, you had x squared minus 9 over x minus 3. Right? Again, what you cannot do is cancel that out and leave one x behind, cancel this out and leave a 3 behind, and end up with x minus 3. That's all of those steps right there are wrong. You're not allowed to do that. Okay? So just be careful. The only thing you're going to cancel whenever you start slashing things out, and you do it with sound effects if you have to, you can only cancel if they're connected to the rest of the numerator or denominator by multiplication. That's the only time you can do that. Now we have we haven't added. We've simplified rational expressions. It turns out that the very next operation that we want to consider doing when we have a rational expression is to be able to multiply two separate fractions or rational expressions together. Okay, we want to be able to multiply those fractions together and cancel those terms out that way. It turns out that multiplying is exactly the same thing as simplifying. So all you're going to do is basically the same steps. You're going to factor all the numerators just like you did in the previous examples. You factor the numerators. You're going to factor all the denominators. Okay. Once you've done that, you divide out any common factors. Now here's the thing. You've done this with numbers before. Like if I had 1/2 times 2/3, notice how when multiplying you go straight across. You multiply a number straight across. This is on bottom, this is on top. It's connected by what operation? Multiplication, so the division will cancel out. You can cancel out things from one numerator and things from another denominator. So across the two fractions you can cancel those things out. Once you've done that, you do like I said, you just multiply straight across. Okay, so let's do this example down here. First thing you got to do is factor all the terms. In this case, 4x minus 5 doesn't factor any further, so I leave that on top. On bottom, x minus 6 does not factor. On top of the second fraction, I can factor. That's a trinomial, so I'm going to use reverse FOIL to factor that. I know this sign tells me it's the same, and the other sign tells me they're both minus. The first term in each binomial is going to be x to give me x squared, and then 6 times 6 I believe works. You check the outside and the inside. Minus 6 gives me a minus 12x, which works. Alright, and then 4x minus 5. Okay, and now cancel, right? That's out. Okay, cancel. X minus 6. X minus 6. Gone. What are we left with? Well, you just multiply straight across. You end up with only x minus 6 on top. And on bottom, you end up with what? Now, if everything cancels, what are you left behind with? And if you say 0, you're going to be wrong because you can't divide by 0. In fact, what you got to remember is that when you divide things out, it's just like dividing something by itself. What's 3 divided by 3? What's 5 divided by 5? It's 1. 1. So whenever everything cancels, you're left with a 1. So x minus 6 over 1 is just x minus 6 because anything divided by itself, anything divided by 1 is itself. Let's do one more example and then move on to talk about dividing. In this example, we have x squared minus y squared over x plus y times x plus 2y all over 2x squared minus xy minus y squared. Again, we see two fractions multiplied together just like in the last example, so we start by factoring the numerators and the denominators. On top here, we see a difference of squares, so we recognize that that is a special factoring formula that will factor as x plus y, x minus y. In the denominator, I'm left with x plus y times, I have x plus 2y in this numerator. And then I can reverse FOIL the denominator for the second fraction. I'm going to have a 2x and an x. I'm going to have a plus and a minus. Let's try y and y. Does that work? I end up with a minus 2xy and a plus xy, which gives me minus xy, so it works. Now we cancel. Bang, bang, gone. Bang, bang, gone. What about these things? Well, they look very similar, but the 2's are in the wrong place. And there's no way to factor things out to get one to look like the other. I cannot turn this into just an x and this a 2. So these aren't alike. They don't cancel. I can't cancel individual pieces because of the plus sign. So that's it. I've got x plus 2y on top and 2x plus y on bottom. And that is simplified. Okay? And just realize the reason why we're doing all of this is that we now have a much simpler formula to work with than if we had started off with just this formula. If I gave you a whole list of x's and y's to plug in and evaluate the formula, ask yourself this: which formula would you rather use? Would you rather use this lengthy formula here or the simplified version? Obviously, we want to use the simplified version, so we want to make sure that we can do that. Now let's talk about dividing rational expressions. Dividing fractions is, there's just a little trick to remember, otherwise it's exactly like multiplication. If you wanted to divide two fractions, like you wanted to take 1/2 and divide it by 3/2, you want to say, what do I have to multiply 3/2 by to get to 1/2. The trick is to just invert and multiply. Right? You see it here with the A, B's, the C's, and D's. What I'm saying is you take the second fraction and you turn it upside down, and then you multiply. So you go back to what you were just saying, what we were just doing before, once we get the second fraction inverted. And that's going to work with big complicated fractions that involve polynomials in the numerator and denominator as well. So all you need to remember on dividing rational expressions is invert and multiply. It's easy because if you've got down multiplying with these fractions, all you got to remember to do when you divide is flip the second one. So what we end up with here is this. We got 12. Let me use the right pen here. 12a squared minus 22a plus 8 all over 3a times, and I'm changing the division to a multiplication, and I do that by switching the second fraction. 2a squared plus 4a divided by 3a squared plus 2a minus 8. Now I'm going to factor. Take this numerator, factor it. Let's see, first thing I need to do before I factor that is I need to pull out a GCF. Right? The GCF here is going to be, I can pull a 2 out of all of those. And that leaves me with a 6a squared plus or minus 11a plus 4. On bottom I have a 3a. On top of the second fraction I'll pull out a 2a, and I'm left with a plus 2. On bottom I can factor this one. So I'm running out of space here. That's going to be a 3a and an a. It's plus and minus. Let's go with 4 and 2. I think that works. 4 and 2. That's negative 6 plus 4 gives me a minus 2. I got a plus 2, so I need to switch my signs. So let me grab my eraser and take out that sign, take out that sign. Oop, I erased too much. We'll put it all back in. I'm going to have a 3a minus 4 and an a plus 2. Okay, so last thing I got to do now is factor that numerator here. So I'll have 6a squared minus 11a plus 4 factors into, let's see, I believe it's a 2a and a 3a. We'll try that. We know it's plus and minus. Let's do, actually we know it's minus minus. Let's try 4 and 1. 1 and 4, I believe, works. Minus 8 minus 3 gives me minus 11, so that double checks. Fantastic. 3a times 2a times a plus 2 all over 3a minus 4a plus 2. Now we begin to cancel whatever's in common. The 3a minus 4 cancels with this 3a minus 4. Bada bing. Those are out. A plus 2s are out. This a cancels with this a. So I'm left with this 2 times this 2 is 4 times 2a minus 1 all over 3 is your final answer on that problem. Okay? Fantastic. Well, that ends section 6.1. We're done with domains of rational functions, simplifying, multiplying, and dividing. We're ready now to start how do we add and subtract these fractions together.